Okay, we're going to look today at section 6.7, which is titled Solving Radical Equations in Inequalities. Okay, so on these problems, we'll be solving, but we're also going to need to check our answer. So number one, okay, we're going to solve 5 equals square root of x minus 2 minus 1. So first thing I want to do is I want to isolate the perfect square. So we can add 1 to both sides. And then once I have my square isolated, I'm going to square both sides. Which gives me 36 equals x minus 2. Now we can solve this equation. So we have our answer that x equals 38, but we do need to check it. And the reason we need to check is that we have a square root, and you don't have an all real number domain on square roots. We have a restricted domain. So we want to test it and just make sure it actually works. So we get square root of 36, which of course is 6. And 6 minus 1 does in fact equal 5, so that works. Now let's take a look at the square root of x plus 15 equals 5 plus x, square root of x rather. So I want to point out that we don't have just one square root this time. We have square roots on both sides. And so what you have to do is make sure one of the square roots is isolated, which in this case, the one on the left is already isolated. So let's go ahead and just square both sides. But on the right side rather, we have something a little bit more complex, so I have to wrap it in parentheses and then square it. So on the left, we get x plus 15 rather, equals, and then on the right, here, we're actually going to have to think about 5 plus the square root of x times 5 plus the square root of x. You cannot just distribute the square. Instead, we're going to have to like FOIL. So 25, and then we have 5 times x, that's a 5x squared. Sorry, 5 times square root of x is 5 square root of x. Then square root of x times 5 is another 5 square root of x. And then lastly, square root of x times square root of x becomes just x. So 5 square roots of x plus 5 square roots of x combined together, to make 10 square roots of x. Now I want to subtract x from both sides. And I'm going to go ahead and subtract this 25 over because I'm ultimately wanting to isolate that perfect square. This brings me to this point. You can now divide by 10. So negative 1 equals the square root of x. So then I would square. I have to square that entire negative 1, which becomes positive 1. X equals 1. But I better check that answer. So I end up with square root of 16 equals 5 plus 1. Well, that becomes 4 on the left side, becomes 6 on the right side. It does not equal. So therefore, we would say that 1 was an extraneous solution. You don't have to write that word down. It appeared to be a solution, but it did not fit in the domain. We had a square root problem, and when we plug 1 in there, we got a negative. That was a problem. Okay, so this time, instead of writing a radical, I have it written in an exponent form. We have a fractional exponent, which we know is the same thing as a radical. So I do have to isolate that first. Now I can't get rid of the 2 or the 3 out of the parentheses. I have to deal with that exponent of 1/3 first. Remember, that's the same thing as a cube root. The opposite of a cube root is a cube, or another way to think of this is take this to the power of 3. You would multiply your exponents. 1/3 times 3 would be a 1, and that's what I want. So I have to do it to both sides. -1 to the third is -1. We get n equals -1. We're going to test it to make sure that it works. Oops. So we plug it into the original. Oh, 1 to the 1/3 means the cube root of 1, -1 rather, which is -1. It does in fact equal 0, so there's our answer. And this one I'm going to add 2 first because I need to isolate that parenthesis. We cannot distribute the 3 because the parenthesis has an exponent on it, so we just have to divide it away. So now I'm ready to cube both sides, giving me 5y minus 1 on the left side. On the right side, you have to cube 2, which gives you 8, cube 3, which gives you 27. Now I'm going to add 1, but I really want a common denominator, so I can think of 1 as 27 over 27 over there on the right side. So 8 27s plus 27 27s. 8 plus 27 is 35 27ths. Divide by 5. Since this is a fraction, I don't necessarily want to divide by 5. Instead, I can multiply it by its reciprocal, which is 1/5. And then my 35 and my 5 can simplify. So I end up with 7 for a numerator, 27 for a denominator. I need to test that. So I would have, that's 5 is like 5 over 1. So 35 over 27 minus 1. Well, 1 is the same as 27 27ths. 35 27ths minus 27 27ths is 8 27ths. I have to cube root both the 8 and the 27. Cube root of 8 is 2. Cube root of 27 is 3. The 3 will cancel out, so you get 2 minus 2, which does in fact equal 0. It works out. Next, I want to switch into inequalities. So there were our equations. We're still going to solve. So we'll subtract our 1. Square. Oops, should be subtracting 2. And I get an answer that x is greater than or equal to 7. However, when I think about the fact that I need to test it, since we're dealing with the square root, there's not really an unlimited domain, so I don't know for sure that that entire region, that everything greater than or equal to 7 actually works. So instead of just circling that, and I'm really not I can't go plug in every number that's 7 or bigger. That's not feasible. That worked in the last couple problems where I only had one number to check. It doesn't work here. So what I have to do is to do something a little different. I have to actually consider my domain or domain if you think about your square root. We know the radicand, or what's inside, cannot be negative. It has to be greater than 0 or equal to 0. And so I'm going to test this just so we know what values are even possible, and then we'll see if our answer actually makes sense. So first we subtract 2, then we divide by 2. So we know that anything, this is telling us anything greater than or equal to -1 is okay. It'll work to plug it in. So now consider our answer over here. We said everything greater than or equal to 7. Well, everything greater than or equal to 7 is in fact greater than or equal to -1. It's okay. Like there's our domain. That's all possible. Then we came along with this problem. We had 7. And we see that, oh yeah, it was all fine. It was allowed within the domain, so not a problem. Let's do another example where that isn't going to work. I'm going to actually check my domain first. I like to do that first. I should probably, I guess before I can check the domain, I have to give you the problem. We're going to do the square root of 4x minus 4 minus 2 is less than 4. Okay, so for that domain, we look at what's in the square root, and we know it has to be greater than or equal to 0. That's always the case because it's in a square root. I would add 4, divide by 4 rather, to get an answer of 1. Okay, now let's go ahead and try and solve the problem. I'm ready to square both sides. So 4x minus 4 has to equal, or it has to be less than 36. Add 4. Divide by 4. We get x is less than 10. So now we have to compare that with our domain. We previously said x had to be greater than or equal to 1. That's what we knew about x. Now we're saying that, hey, our x, the one that actually works in this, has to be less than 10. So 10 would be over here, and we're saying an open interval and go less. Well, it's okay. All of that works until I get to 1. Anything to the left of 1 no longer is in the domain, and so that we have to throw that out. So to kind of synthesize this, we know that everything over there doesn't work. Anything to the right of 10 doesn't work, so it had to be in between those two. So we had a closed interval at 1, an open interval at 10, and everything in between those was our answer. So since it's in between, that's an and. The way we write that, 1, it's closed interval, so less than or equal to our x, less than, not equal to, 10. There's the portion. That's our solution set. Those are where the numbers are located that work both in you're allowed to plug it into a square root and it satisfies the problem. So we had to restrict that solution down because of the domain. Okay, hopefully that gives you an idea. You're going to need to do some practice on this, especially on problems like that last one, trying to understand when you restrict down your solution set. Practice is going to be key.